Okay, now I am recording. So I have gone over what you have submitted, and Olivia, do you mind if we go over your assignment? Because I think it's quite good, and I will take the data from there. Olivia, well, uh,
Yes.
yes. Do you mind if we if we go over your assignment? Because
No, I don't
I
mind.
have to take. Okay, great. So this is your assignment. There, most of it's good. It's quite good, but there are some mistakes and there's something missing. So I want to go over it. So this is your first slide. Here you have 26 people and 107 people. Okay. And this is the assignment. This is what we have to do. And we have first we have to understand what we are doing. Um, we have two different floors here with two different rooms. We have only one air handling unit. And this week, when we are working, we will be working with Revit on Thursday. So this week, you will get to know what the variable air volume is, and we can work with that variable air volume in Revit as well. Okay. But these are devices that control the flow. Here we have this flow because we have only 26 people, and here we have a different flow, and we have the same air handling unit connected to those two different rooms. Okay, so we need a device here because if we didn't have this device, there wouldn't be a way to control the amount of airflow that goes to this room or to that room. Okay, so the system has to be intelligent, and someone has to tell the air handling unit that they need this flow 107 plus 26, and this is the total flow. But there's something here that, okay, so here I only need 26 people, and here I need 107 people. So this is the variable air volume device. So we need both of them. Because people, or a number of people, changes during the day. Okay, so in a school building, yeah, if we are working with a school, it's very clear because we have a class in this room, and then we go out, and then 30 minutes later we have a different class with different people. Okay, so working with a school building, it makes us understand that we don't have the same occupancy throughout the day. So the people occupying a class changes. Why? Because there are different students registered in different courses, and we have schedule. So we have a class from 8 to 9:45, and then the following class it starts at 10:30, and there is nobody between 9:45 and 10:30. Okay, so we need sensors, and this information, it's yeah, so we need to communicate this information to the air handling unit, and then the air handling unit will pump the amount of air that we need each time. So that's the difference between an intelligent, we can call an intelligent system, and a non-intelligent system. Anyway, things are getting better, and now because we can work with sensors and the price of sensors has dropped, we can place a lot of sensors throughout the building, and then we can send this information to the air handling units or the boilers or so everything's connected. So that's why we need now in buildings, we need software engineers. Let's say 50 years ago, we didn't need a software engineer in buildings. Why do we need a software engineer? Because now software, especially in public buildings, in buildings where the occupancy is large, and it's not only that we have a large occupancy, but it can change over the day. Okay, so we can have 100 people, then we have 20, then we have 0, then we have 200. So when we have these kind of buildings, the software gets more and more, it's more and more complicated, and yep. So it's this is what we have to do now. We are not designing the software for, we are the architects. We are not designing the software. We are designing the system itself. So we are affected by the width or the diameter of ducts. And of course, if we want our building to be good enough, we need to deal with the mechanical engineers and software engineers because otherwise we won't have any control over this. Okay, so we have to collaborate. Now, designing a building, it's a multidisciplinary task. So now architects, unless we are working with single family houses, it can be a one person task. But when we are working with complicated buildings, then we have to collaborate with especially with other engineers. Okay, so this is, we have 26 people and we have 107 people. Okay, so what have we done here? First, we need to calculate the CFM, okay, the cubic feet per minute. I told you that it's always 20 CFM per minute. Well, today I want to explain where does it come from. So we have this chart from the ASHRAE. The ASHRAE is the Bible of the HVAC systems. It's the ASHRAE is American Society of Heating, Air Conditioning, Ventilation Engineers, or whatever. Okay, so it's the ASHRAE. I think I've talked about ASHRAE before, but all the answers to our questions are here in ASHRAE. No, not here. Oh, we have the Spanish chapter. Okay, now everything's about COVID, and well, all these things that we are talking about now, ventilation, it's very important now when it comes to control the COVID, because if we don't ventilate the houses, we have more risk to get infected. Okay, so it's not just an architecture issue, it's just a health issue. Everything we are talking about ventilation this year. Okay, so in ASHRAE, this is in Spanish, but well, ASHRAE is an American association, so they have chapters everywhere. But all the things are here. So we have a lot of things. We have events, we have resources, all the things. Okay, so ASHRAE, it's a good. You can become a member of ASHRAE if you are an architect or if you are an engineer. And if you are a member of ASHRAE, you have discounts. They have a lot of software tools that if you're not a member, you have to pay for, but if you're a member, they are for free. So there are a lot of advantages being a member of ASHRAE. Anyway, this is taken from ASHRAE. And as you can see here, we have the CFM per person for different uses, different building uses. Here we have commercial, hotel, office, public spaces, showrooms, institutional, education, residential, or private dwellings. Okay, so the residential means well, we have private dwellings, but residential buildings are apartment buildings, usually, okay? Anyway, here you have the CFM per person. And as you can see, most of the uses are either 20 or 15. So this is in cafeterias or fast food or dining rooms. You will have 20, in kitchens we have 15. In conference rooms we have 20, in lobbies we have 15. Here we have 20, 15, 20, 15, 20, 15, okay? In 80% of buildings, the CFM it's between 20 and 15. This is the minimum CFM per person. So if you have 15 and you use 20, it's fine. It's even better, okay? And where do we have other figures? Okay, so in bar and in cocktail lounges, we have 30. Well, there are a lot of people drinking and, I don't know, dancing or whatever. And when there are a lot of people and we need to control the air quality, we need to increase the CFM per person. Okay, so in bars, we have to increase this 30, it's fine. Then in gambling casinos, yeah, it makes sense. There are a lot of people there, they get excited, they okay, so it makes sense that it's more than 20. Then we have 60 and 50 in public restrooms. Yeah, we need to renew the air of public restrooms, makes sense. And smoking lounge. Yeah, okay, so it's, everything that has to do with smoke, we have to increase the CFM a lot, okay? And what else? Well, here in operating rooms. Okay, so in if we want to have a surgery in an operating room, the air quality has to be really good. Okay, so that's why we have to increase the CFM. But other than that, other than bars, smoking rooms, casinos, and operating rooms, if we use 20, that's fine. Okay. But where does this 20 come from? It comes from ASHRAE. So I'm not making up anything. And it can be between 20 and 15, but again, 20 it's better than 50. Okay. So this is where this 20 CFM comes from. Then we need to multiply 160 people times 20. So this is the cubic feet per minute for the first floor and the second floor. Then we need to calculate the enthalpy. Okay, so the enthalpy, where do we calculate the enthalpy? We need the indoor and outdoor conditions. So here indoor, it's 70 and 40. And outdoor, we have winter and summer. So we have 30 in winter, 80% relative humidity. In summer, 100 Fahrenheit, 25% relative humidity. And then we have to calculate this, well, we have to calculate the specific volume, which is always around 30. This is 12.4, this is 14. Well, when it's too hot, this specific volume, it's but between indoor and outdoor conditions in winter, we are around 13. So this is 12.4 or 12.5, and this is 13.5. So around 13 goes well. Okay. But we have to calculate the enthalpy, the indoor and the outdoor enthalpy. So we have to open this the psychrometric chart. Remember that first we need to work with settings, English, preset inputs, submit. Now we have everything with Fahrenheit, imperial units, and we can calculate enthalpy of, we can either use the first one, the basic one. So here, if we type 70, and what was the relative humidity? 40. Sorry, 70 and 40. We click here, we submit, and here we have the enthalpy. Where is it? Enthalpy here. It's 23.6. Okay, so here we have 23.6. For the outdoor, in winter, we are going to work with the winter example. So it's 10.2, let's see. So this is 30 and 80. So we go back here, we type 30 Fahrenheit, 70 relative humidity, submit. And the enthalpy is 9.8. Oh, because it was 80%, sorry. 80%, submit. And now the enthalpy is 10.18, so 10.2. Okay, so that's correct. We have the indoor and outdoor enthalpy. We are working with winter. In summer, it's the same. We have to type 125 relative humidity, and that will be the enthalpy. Okay, so we have the CFM of the first floor. We need this CFM for the first floor and the second floor. And then you have calculated the pounds per hour. That's important because in our in this, if we go to process, okay, so you see that we have to introduce here the airflow in pounds per hour. So we have to turn these units, cubic feet per minute, into pounds per hour. So we have to multiply times 60, and we have to divide by the specific volume, which is around 30. It can be 30.4 or 12.6, whatever, but it's around 13. Okay. So here we can introduce the pounds per hour, the airflow of the first floor. We are working with the first floor. Okay. So that would be 9,877. Okay, so here in this tab in process, this is 9877. And now we have to type here point A and point B. Okay, so this is A, let's say that it's outdoors, and B is indoors. So we get rid of all those elements here. This is the first one. So that would be outdoors. Outdoors, it was 30 Fahrenheit and 80 relative humidity. Okay, and then the second one, it's indoors, so it's 70 and 40. Okay, so those are outdoor and indoor conditions. Point A is outdoors, point B it's indoors. Okay, here we have to include the dry air flow, and we only have to submit. Yep. So if we submit, oh, we have to compute and draw processing plan. Yeah, so we have to click here. So, okay. So this is the heating load. Cooling load, we don't have cooling load because it's winter. Okay, so we don't have any cooling load. This is the outdoor. These are outdoor conditions. This is our indoor conditions, and the arrow goes from indoors to outdoors. And the heating loads are 2,215 BTU per minute. Okay, so this is the heating load that we need to heat up that air from that condition to that condition. I don't know if you have calculated this. Okay, so you have, yes. So this is the first floor. Well, we can calculate this different ways. We can do this, what you have done here. Okay, so this is the airflow, and then we have the indoor minus outdoor enthalpy divided by the specific volume. Okay, so this is what you have done here. This is the CFM, cubic feet per minute. This has to be per hour. So we have to multiply it times 60. And then this is indoor enthalpy minus outdoor enthalpy divided by the specific volume. So the BTU hours are 132. What was the value here? This is BTU per minute. Okay, so we have to multiply these times 60. So let's see if it's the same. Calculator. So if we multiply 2,215 times 60, so this is 132,000. And your result was 132. Okay, that's fine. Okay, so there are two ways to do this. We can use this formula, or we can use the process tab of this chart, and just by including here the dry air flow in pounds per hour. Here we type the indoor and outdoor conditions. We click compute and submit. And this is the heating load. And both results should be similar. I mean, it's around 130,000. Okay, so you have done this for heating power in winter. You have done for the first floor, for the second floor, and we have done this, the cooling power in summer for the first floor and the second floor. And then you have calculated the energy. Okay, you have done this with the formula, and I have done the same thing, and I have gotten the same result by using this process. Okay, anyway, we have to use this, either the basic. With the basic, we calculate the enthalpy, and then we can apply the formula that it's airflow times enthalpy indoors minus enthalpy outdoors divided by the specific volume, or we can just use this process tab, and we calculate the heating load here, whatever works for you. I don't mind, because as you can see, results are the same. Okay, but there's something that it's not here as far as I understand. Yeah, it's not. Because this is then you have calculated the energy. Okay, so just multiplying power by times time. So you have the total power here times 24 hours, and then we have the energy. Okay, that's fine. But this is the air handling unit without the heat recovery. That, as you can see here, now we have the heat recovery. So what does it mean? It means that we recirculate this return air, and we extract part of that heat. Okay, we are preheating or pre-warming the outdoor airflow that goes through this heat recovery device, and then we save energy by doing this. What is the energy that we are saving? The energy that we are saving, we have to calculate it with cycle 1. Okay, with cycle 1, as you can see here, we mix these two airflows, the fresh and the return airflow. So we mix these two, and we extract part of the enthalpy that we have in the return, because the temperature inside it's 70 and the temperature outside is 30. So we are heating up this fresh air for free. Okay, so this is what we have to do here. How can we work with this? Okay, so here we have to type temperature indoor, 70, relative humidity indoor, 40, dry bulb temperature outdoor, 30, relative humidity outdoor, I think it was 80, G vent diff, let's say 0 here. Here the fresh air ratio. Here we have the 15%, means that we are using only 15%. I told you that everything, it has to be above 50. So if we have a good heat recovery, it has to be above 50. So we can use here 50, okay? Heat load. If we are applying an extra heating load here, we can type something. Otherwise, we can type 0, okay? Because we want this to be for free. So, and then we have the ventilation flow. Okay, so we have to type here winter, and then this ventilation flow in pounds per hour, it's activated. So what was the ventilation flow? If we are working with the first floor, we have to type this ventilation flow, 9,877. 9877. Okay, now we have to compute and draw, and by doing this we submit. Okay, and here we have a heating load. So this heating load is 1,000 in BTU per minute. We have to turn this into BTU per hour, so it's 1107 times 60. Okay, so it's 6624. So on this, when we are calculating the heating power in winter for the first floor, we should add with heat recovery at 50%. So that depends on the efficiency of the heat recovery. It can be above 50, it's good. So it can be 50, 60, whatever. But just to be conservative, let's use 50. So with heat recovery, the power in BTU hour will be 66, 66. 66,440, I think it was. BTU hour, which is it has to be like half this power. Okay, that means that we are working with this heat recovery. We are using only half the energy that I need. Okay, so it makes sense, and it's worth it. Okay, it's worth using heat recovery because I'm saving half the energy that we need for ventilation, and that's a lot. Okay, so this is what is well, we didn't have this, so we have to include this without and with heat recovery. So that would be without heat recovery. Okay, and that will be with the heat recovery. And then you have to do the same with the second floor for winter and for the first and second floor in summer. Okay, but what we are doing is first we need to calculate the CFM, so the ventilation load. It depends on the number of people. Well, it depends on the use of the building, but unless we are designing bars or gambling casinos or smoking rooms or whatever, it's 20, it's fine. So we don't have to, we have to use this and that's it. Then we need to see what we are doing. If we are recirculating this air, we are using this heat recovery. Okay, so we have to use the heat recovery option or this cycle 1 option because we are saving energy. If we are working with this kind of building, with public buildings, it's worth using this. In single family houses, well, I would recommend using a heat recovery for single family houses. But I can understand that people don't use heat recoveries in houses. Okay, I can understand that because savings are not huge. But in public buildings, savings make a difference by using heat recoveries. And that's it. And what's next? What's next? Then we have to work with the schematic. Okay, so there were two options here. This option was with the ground source heat pump. We know that we have those boreholes or this buried loop, whatever. It can be shallow or it can be deep. Shallow, it's that it's buried like 6 to 10 feet, and the deep borehole, it's around 200 feet. Okay. Anyway, the deep one is more effective, but the other one is cheaper. The shallow one is cheaper. So it's up to the client, the company, the architects. We have to deal with it. But we need this. We have the evaporator, the condenser, the expansion valve. It's not the compressor there, but well, we are not studying heat pumps. This is not our job. We are using this as a black box, and we connect these two pipes there and these two pipes there. And then we connect the ground source heat pump to the air handling unit. And then from the air handling unit, we have air, supply, and return. Well, to be more accurate, we would need like another pipe, another return pipe here. It would be here. It seems that the same pipe or the same duct is for supply and return. Well, in theory, we need two different pipes. Okay, but this I can understand this. Okay, so we have the two space, two floors. The air handling unit is on the top of this building. This device would be probably in a mechanical room, and it's connected to the boreholes here, and it's connected to the air handling unit there. So that's correct. And the other option was this. We needed the chiller and the cooling tower. And then we need to connect the chiller to the air handling unit. And we need to connect the condenser to the cooling tower. Can it be better? Yes, everything can be better. For example, now we should know that the chiller is on the basement, but the cooling tower should be on the top. The air handling unit is always on the top. Well, it's always. Usually it's on the top of the building, but the cooling tower is always on the top of the building. So if we are doing this for schematics, it's okay because we are just connecting this to this and we're connecting this to that. But if we place this close to the air handling unit, it will be, well, close to the air handling unit. We place this here because in theory this is on the roof, and okay, that will be clearer. Okay, but for this kind of schematics, the order in theory doesn't matter because everybody knows, well, everybody, mechanical engineers know that the cooling tower should be on the top of the building, on the roof. So okay, so this is the cooling tower. They assume that this cooling tower is on the top of the building, and that's it. And they know that the chiller, it's on the basement. Okay. So that's it. So this is, well, then from this air handling unit, just to make it perfect, you should have added the ducts, okay? Because why don't we add the building here, the same thing you have done here? So you should add the building here with the first floor, second floor, and ducts from the air handling unit. Okay, so this is what you have to do. Olivia, you are good so far. You have done everything. Calculations are correct, but you have to include now this calculation using the heat recovery. Okay, using this option of cycle 2 with this, with this psychrometric chart, you have to use this option. Well, I told you that this is the first part of this midterm assignment. So if you haven't done it yet, please do it. If you have any questions, get back to me. I will meet with you if you need it, and I will help you solve the issues. Or if you don't remember how to use this chart, I'll help you. But now we have to calculate. So on this assignment, we have done this. So we have calculated the airflow. We have calculated the power of the cooling and the heating coils. And we have connected this heating coil either with a ground source heat pump or with a, by the way, the heating coil, okay, one of the options, yeah, it's not there. When you're using a ground source heat pump, this can provide heat and cold, so we don't need to duplicate the devices. Okay, so we can use the ground source heat pump in winter and summer. But here, in this one, this is for cooling, but you don't have the device for heating up the air here. So you need, I think it was written that you have to use a pellets boiler. So you have to place here a pellets boiler, get rid of the smoke or the gas of the gases, and then you have to connect this to the air handling unit. Okay. Because we need a heating system and we need a cooling system. If we have a chiller, it's just a cooling system. If we have a heat pump, ground source heat pumps, everything that it's like this heat pump means that it can be used for heating and cooling. A chiller is a heat pump that only cools down the air or whatever, or water, whatever. Okay, but if we're using a heat pump, this can work either in winter or summer. The problem with this is that this ground source heat pump cannot work cannot heat up or cannot cool down at the same time. And sometimes we will see if we have a very big building with different rooms or in different uses, we might need cooling in one of the rooms and we might need heating in other rooms. Okay, so this is difficult to understand, but we will explain examples in which we would need heating and cooling at the same time in the same building. Then we have to duplicate systems. Okay, so this is acceptable if we know that we are not going to use heating and cooling at the same time. But if we're going to use heating and cooling at the same time, then we need to duplicate the systems, because we need a system for heating and we need another system for cooling. Some of the air handling units can be providing the building with heat, and other air handling units can be providing the building with cool air. Why? We will explain that. But in large buildings, that happens, and especially in office buildings, that happens. It depends on the occupancy. When we have a lot of people working on the same area, probably we need cooling. If there are only a few people working in that area, we might need heating. So if we can't control the number of people, because in office buildings, one office can be full of people and the other can be half empty, or so we might need different. Yeah, we might need cooling and heating at the same time. Anyway, in this case, here we don't have anything that heats up this air handling unit. So we need the boiler, and then we need to connect the air handling unit to the boiler with another loop like this. Why am I? Okay, yeah. So we have calculated the heating and cooling power. We have calculated the heat flow, but now we have to calculate the duct work. And the duct work, there is another parameter that we have to control, which is the air speed or the air velocity. Okay, why? Because if we have a high speed, we will hear this. We will hear something like that through the pipes, and this is not pleasant. Okay, so sometimes you don't in public buildings, you don't know or you don't notice the amount of noise that you are exposed to, and yeah, so you get used to it. So if there's like an airflow, so in 5-10 minutes your brain is okay, so this is it, there's an airflow here, there's a noise, but it doesn't bother me. Well, it bothers you, but you don't notice that. Okay, so you are processing a lot of things in your brain, and sometimes when you don't notice how much noise there is in that room until when it stops, and suddenly it stops and you say, silence, it's wonderful. Okay, so that happens because the air flow through the pipes is too fast, or the speed is very high. We have to control this. What if we have a very low speed? Okay, so if we have a very low speed, because this we need the air that flows through the diffusers. We need the air to go through the room, and it has to exit that room through the return diffuser. If this air speed is too low, this airflow doesn't get here. So the airflow stops here, and we have what we call stagnation. Stagnation means that the air is stopped. And this is not pleasant because we are not renewing the air. We are not getting rid of the exhaust air, and we are not supplying enough air. Okay, so when that happens, we don't have comfort, and eventually we will have bad indoor air conditions. So the speed has to be within limits, so that we don't hear a lot of noise because of the high air speed, and we have enough ventilation and the air goes from this diffuser to that diffuser, because the air speed or the air velocity is good enough. Okay, so it's very important that we control the speed, the air speed or the air velocity within the room and within the ducts. Okay, so this is what we are going to do today. There's a velocity method that relates three different parameters. Q, it's the airflow. It's the CFM that we have already calculated. So in this example, so this is the CFM on the first floor, the second floor, and then if we add this up, it's the total. Okay, so this is the CFM, 2,140 plus 520. So this is Q, the airflow. Then we have the area of the duct, and then we have the speed or the velocity of the air. Okay, as you can see, the formula, it's quite simple. So the area of the duct equals airflow divided by velocity, or if we want to calculate the velocity, that equals the airflow divided by the area of the duct. This is the formula in international units. In imperial units, it's always more complicated. It's not that complicated, but it's more complicated than this because we need to add this factor 144. Why? Because of the units. Because we are working in here, the air duct, it's in inches square, but here we have cubic feet. So the relationship between feet and inches, yeah, because the airflow is usually measured in cubic feet per minute, and the area is measured in square inches. Okay, if everything were either cubic inches divided by minute, or here we had square feet, we wouldn't need this 144. Anyway, the usual units are inches for the ducts and cubic feet for the airflow. And finally, we have the speed. The speed is in feet per minute, the air speed. Okay, so this is a very simple formula. It depends on the airflow and the area. So if we want to reduce the air speed, what do we have to do? We have to increase the area. That makes sense. Okay, so if we have a wide duct, the air can flow there very slowly. But if we have a very narrow duct, the air is going there very fast. So that's it. That's the only thing we need to understand today, that the more the speed, the less the area, or the lower the speed, the larger the area. These are the things. And here we are working with these thresholds or with these limits in meters per second for international units, or feet per minute, okay, in imperial units. Here we have comfort systems, industrial systems, and high-speed systems. What is this? So there are different velocities, recommended velocities for each different use. When we are talking about comfort systems, these are buildings. Industrial systems, it's well, it can be buildings, but buildings, industry buildings. So again, it's not a residential building. It's not a building where people stay or people work. Industrial systems, it's in factories. We might need conditions to manufacture cars or whatever. So in this kind of industrial system, we have other velocities. And for high-speed systems, well, I don't know, probably if we are working with planes and we have to take off and the turbines and all that stuff, we need another. But these comfort systems is for buildings, okay? For buildings where people are living. We can have a building with industrial systems, or we can have a building with high-speed systems. But it's not buildings for people. They are buildings for other uses. Okay, but when we have people, those are the velocities that we have to abide by. And as you can see, we have different kind of branches. We have branch ducts, or different kind of ducts. And we have the main duct, the main branch duct, or the branch duct. What is this? Well, it depends. I think it's easier to understand that the low velocity is for ducts that are close to people. And those main ducts, or the higher velocity, is for ducts that are not in contact with people. Okay? How can we explain that? I think if we open Okay. If we open the Revit file that we worked on Thursday, we can understand this. Takes time. Okay. So if you remember the masterpiece we designed on Thursday. So what is looking at this, what is the branch duct? So something that it's close to people with the lower velocity is. So I would say those are these ducts or even these, okay? It depends. If it's exposed, if this duct is exposed, I would use this as the lowest velocity, around, yeah, from 200 to 500. Yeah, so 400, 300, 400, that's fine, okay? And what is this main duct? The main duct is a duct that comes out of the air handling unit, okay? So nobody's living here because this is on the roof of the building. So nobody lives here. So in this duct, I think we can afford this velocity around 1000, okay? And these main branch ducts, this can be a main branch, okay? So we have this vertical duct. It's not in contact with people because usually it's this is within a shaft or a space that goes from the first floor to the top of the building. So if I had to say, but this is inside the building, okay? So if it's inside the building, but it's not in contact with people, I would use something close to 700, okay? If it's out of the building, I would use 1000 or more, 1200, 1300. And if it's in contact with people, if it's within the room, and especially if it's exposed, then I would use 200, 300, no more than 500. Okay, so if you look at the TDS center, the classroom, the 110 classroom, where we used to have this lesson, there are exposed ducts there. And even in the computer lab, you can see that we have two round ducts in one side and the other side, and they are exposed. They are not hidden by the false ceiling. So the air velocity should be close to 200, 300. But the ducts that are outside the building on the roof should be around 1000. Okay? Those are recommendations. So it's not sometimes, because it depends, because the more or the higher the velocity, the smaller the duct. And sometimes we have space constraints. Okay, so we cannot afford having I don't know, a 20 by 20 inch duct because I don't have enough space because the distance between the floor and the ceiling is too low, so I can't have a duct like this. So it has to be lower, and then the speed has to be higher. Okay, it depends, but we need to at least we need to realize if we are doing something right or wrong. So those are recommended values. And the good thing in Revit is that we can check. I told you that last week we designed this ductwork, okay? And now we have to check whether the speed limits are right or wrong. So if you remember here, by selecting the diffuser, here we have the CFM, okay? So it's 750 CFM. We decided this because well, we did this exercise last week, and we ended up realizing that we needed. I think the total CFM of this floor was 3000. So if we divide 3000 by 4, so each diffuser is 750. Okay. So now, what about this duct? So in this duct, we have the flow, 750. That makes sense. In this duct here, it should be 3000. Yes, it is 3000. So that means that we have connected everything well. And finally, we have 3000 and 3000. Here, it should be 6000. And it is 6000. Okay, so this is to check that all connections are good and we have connected all the diffusers to the air handling unit. Perfect. Now we have to check the velocity. So let's start checking the velocity here. So if we select this duct, we know that it should be around 1000 or 1200 or 1300 maximum. What is the velocity here? 2100. Oh. So it's not acceptable because it's too, well, it's outside the building. Well, we might say that it's outside the building, it doesn't matter. Okay, but if we want to do this we should change this. Okay, so if the air velocity here is 2100, it should be, yeah, it's double that the recommended velocity. What can we do? We have to make this duct bigger. So let's make it bigger, 30 by 30. Look. If we click here now, okay, now the speed or the velocity, it's 960. You see here, 960 feet per minute. Well, it makes sense because now it's within the limits. It's, yeah, it's 960. So it's between 700 and 1300. Perfect. So this duct should be 30 by 30. What's the problem here? Here we have the same flow. Okay, so with this flow, again, the speed here is this, so it's not good enough, as you can see. Okay, so that should be 30 by 30 as well. What's the problem? Connections are not valid. Why? I think I told you. We need this. If we have this elbow, we need a radius. So if the duct is too big, probably we cannot bend this duct. Okay. So what can we do? What can we do? What if we use here 25 by 25? Okay, let's see the speed. It's 1300. 1380. And this is 1382. Okay, I accept this. So what if I use here 25 by 25? Doesn't work. So now I have to do something that I don't like. I have to use ducts that are not square. But what if I have 30 by 20? What is the speed? It's 1400. Well, I can say, let's say 32, 33. Okay, now it's within the limits. It's 1300 now. And this duct is now 33 by 20. Okay, what about this? Can I make it 33 by 20? No. So there's an issue here, and probably I should make something different. Okay, so now I have to modify the duct because, well, I know that this goes well. This is 33 times 20. Yeah, I can accept that. And what if I change? Well, let's analyze this duct here. So the speed here is 1080. What is the recommended? This main branch duct should be below 900. Okay. So I think I can make this, let's say 30 by 20. Okay. If I make this 30 by 20, now the velocity here is 720. 720, it's within that limit between 600 and 900, so it's good. Okay, so that works well. But what is this? Oof, I have to delete everything again because I have connections here that are not well done. Okay, so now I have to connect this one to this one. Can I do it? Let me drag it here and there. Let's see. Oh, look at this. This is 33, because this is 33 by 20. Yeah, it's very unlikely that I can connect something 33 by 20 and this 30 by 20. So let's change this to 33. And now let's try to do it again. Okay, now it works. Okay, so you see how, well, I have to start fixing things because the first approach was good, but it wasn't good enough. What about this, by the way? So this is a branch duct. So the speed here should be below 600. And what is the speed here? It's 3,000. Wow, it's too much. Okay, so now I have to connect this to this. This is 33 times 20. What if I make this 20 by 20? What's the speed here? It's 1,000. It's too much. It's too much. What about this? Okay, this has to be 20 by 20. When we are doing this, we have to fix one by one because now this is 12 by 12 and it has to be 20 by 20. Okay, but it's good enough. So now this branch 20 by 20, it's 800. We are getting better. I think this should be 20 by 20 as well. 20, 20. This connection is 20, 20. It's not 11, it's 20. Okay, there you go. So this branch now, well, it's okay, it's 540. Yeah, so it's below 590. Okay, so I think this is good. This is not good enough. So I would do this 25 by 25. So if this is 25 by 25, this is 690. Okay, it's not that bad. But what if I try to connect this to this now? Will it be able? Okay, I have this connection here now. So now if I select this, okay, it's well connected because we have here 6,000 CFM. The velocity here, it's 1,300. It's within the limits. The speed of this duct is 654, which is within those limits. And that branch should be below 600. So this one, okay, it's 691. Okay, we're getting there. But as you can see, well, this is difficult. Okay, so we are working with Revit, and we can try and check what we have done. I think it would have been better before starting this. We could have calculated this quickly with this formula. Okay, so the speed here, v or velocity, equals 144 q divided by area. Okay, so the area is okay, we can either calculate the speed or we can calculate the area. If we know the speed, okay, we can see what area we need. So let's do this with the formula. Okay, so we know that the airflow, it's 144 times what is the CFM here? The total CFM, it's 6,000. Okay, so it's 6,000. And we have to divide this by the speed or the velocity. And what is the velocity on this main branch? It should be, yeah, around 1,200. So what's the area here? It's 144 times 6,000 divided by 1,200. So it's 720. 720 inch or square inch. Square inch. So if it's a square, the square root of this is 26. Okay, so we are doing this just before doing anything else. We just calculate this. So the duct should be around 26 by 26. Here, my duct is 33 times 20. Okay, why not? Can be. But before designing anything, because otherwise we will have to change all the ducts again. So we can calculate the airflow that we have in this main duct or in this branch duct, sorry. So the airflow here is 3,000. The airflow here, it's 6,000, okay? So by doing this simple calculation before, I have an idea of what the size of my ductwork will be. Then I can change it. I can change it in Revit, or I can well, I can make decisions in Revit. But at the beginning, I should have made the decision that if you remember that we edited that type for this air handling unit, the supply air, 20 by 20 doesn't work. It works with 33 by 20. There you go. Okay, so now we don't have an extra element here. We don't have a reduction because the exit or the supply outlet of this air handling unit, it's 33 by 20. Okay, but you know what we are doing now, so it's difficult. I mean, dealing with this ductwork is difficult. So it was difficult to connect everything and to make sure that the final flow here is the total airflow that we have in these two floors. Okay, but we did that. But now we have to check the velocity. And by checking the velocity, okay, so we have to make it bigger. It's about experience. So when you have done this many times, you see, okay, this CFM and this is the duct area, kind of, and you don't have to think about it. But when we are not experts on that, we either do it by hand, so it takes forever and it's a nightmare, or we just make this rough calculation with the total CFM, and then, okay, what is the maximum area? So the maximum area would be this, okay. And then we can go, as you can see, the farthest the element, the thinner the duct, okay. So the farthest the air diffuser, the thinner the duct. So we calculate the maximum airflow. So we know that this is going to be our biggest duct, okay. So keeping that in mind, it's very important because my duct won't be bigger than this. And I have made that calculation before starting designing the system. Okay, it works. Because otherwise, for example, if you have elbows like this, and you want to make it, let's say 30 by 30, it doesn't work because this is not working. We don't have space for the elbow, okay? And then we find out that 20 by 20 is not enough, and we need 30 by 30 here. So we can change this 30 by 30. Okay. Now we can change this edit type, this return inlet to 30 by 30. 30 by 30. Edit type, return. Well, I don't know. Anyway, if we have to make this is 30 by 30. So we draw duct. I think if we use the elevation will be better. So that would be the south elevation. Yeah. So if I draw duct, so I have to go up, then I have to go this way, and then I have to go that way. Yeah, but this height has to be So it has to be higher, because by doing this and doing this, look, it doesn't work because this is it's not high enough. So I have to go higher, and then I have space for the elbow. Okay. So again, knowing this at the beginning, it's better, because if we have to change that, then we won't have space for the elbow, and then we have to modify all the duct work again. And now here, this is 30 by 30. The speed, the velocity is 960. It's below 1,000. It works. But now this is not working because the velocity here is 3,000. It's too much. Okay, so this has to be thicker. Usually those are symmetrical. If we have the same number of diffusers, of supply diffusers and return diffusers, the ductwork should be symmetrical and it will work. Okay, so if we had trouble with the speed here, we will have trouble with the speed in the return system as well. You might think that this is a nightmare. You are young and unaware, because when I was a student, we had to use tables like this for each single duct. Okay, so there are a lot of parameters here. We have the Reynolds number. We have to differentiate whether we have a laminar flow or a turbulent flow. We are in this system or in that system, and then we have the rugosity, the relative roughness of the. There were a lot of calculating this. It was a nightmare. I had to suffer this when I was a student, and then when I became a teacher, I enjoyed looking at my students suffering. But now I'm not that way anymore. So I'm telling you how to do that with Revit, and with Revit, we don't have to calculate things. We have to check. Okay, so if it's okay, that speed, it's too high. Let's make it a little bigger. Oh, I have to change the. Yeah, so we have to change things, but it's much easier than calculating everything by hand and then drawing the ductwork by hand as well. So we have, yeah, life is much more easier now than it used to be 30 years ago without Revit.